Good afternoon, everyone. I hope everyone can see and hear me. Zeynep, can you hear me?
Yes.
Okay. I am Maria Grazia De Angelis, and I'm hosting this first EMS webinar of 2022 with the technical help of Marco Stoller and Elena Tocci, and on behalf of the European Membrane Society Council. I'm very happy to introduce our first speaker of the year, Professor Zeynep Çulfaz-Emecen. I hope I'm sure I've not pronounced it correctly, but I could have
Very
done worse.
close.
Okay, she is an associate professor in the chemical engineering department of the Middle East Technical University in Turkey. And she got her education, undergraduate education and master degree from the same department, while she got her PhD from the University of Twente in the membrane science and technology group. Her research nowadays is about the development of membranes and membrane processes for enhanced separations in the chemical and biochemical field, in particular for water treatment and purification. And today she is going to talk us about cellulose membranes. And cellulose is a widely available natural polymer. And she is particularly interested in exploring new ways of fabricating membranes, which I guess is also the topic of today's webinar, right?
Yes.
Okay, so I think I'm done for now. If you have any questions, you can type them in the YouTube chat, and I also ask you to subscribe to our channel, to the European Membrane Society channel. And with this, I am done, and I leave the floor to Zeynep.
Thank you. So, am I sharing the screen? Yes. Okay. So I hope all is well with my screen and my voice. Maria Grazia, thank you very much for the introduction and also the invitation, and also everyone who's listening. Hello. So today I'll talk a bit about the work we have been doing at METU on cellulose membranes, focusing on their applications in organic solvents, and also a new membrane fabrication method without the use of organic solvents. Sorry. Okay. So the first thing to mention about cellulose as a membrane material is that this is actually far from being a new idea. In the early years of where membranes were being developed, actually all membranes were made from cellulosic materials at the time because these were the only available polymers. These included desalination membranes of reverse osmosis, hemodialyzers, and microfiltration and ultrafiltration membranes used for water sanitation. These were typically made from cellulose derivatives such as cellulose acetate or cellulose nitrate, because these could be easily dissolved in proper solvents to make into membranes. Cellulose membranes could also be made by derivatizing cellulose and then regenerating it back to cellulose during the fabrication process, such as the cellophane hemodialysis membranes that are shown here. And then in years, these were mostly replaced by synthetic polymers. For instance, the RO membranes, the cellulose acetate RO membranes were replaced by interfacially polymerized polyimide membranes with better permeance and better resistance against biological attack, but poorer chlorine tolerance. Microfiltration and ultrafiltration membranes were replaced by PES and PVDF with better thermal, chemical, and biological stability, but were more prone to fouling. And hemodialysis membranes were again replaced by polyether sulfone or polysulfone with better biological inertness compared to cellulose. Now, after more than half a century later, with new developments in cellulose solvents and with cellulose-based nanomaterials such as cellulose nanocrystals or nanofibers, we want to reconsider cellulose as a membrane material. So within this context, I will talk about three different ways of fabricating cellulose membranes. The first is making cellulose membranes by using cellulose ionic liquid solutions with phase inversion, which is actually the most common membrane fabrication method, but could actually become more interesting and perhaps applicable with developments in ionic liquids as cellulose solvents. In the second part, I will talk about converting membranes made from cellulose derivatives into cellulose. And then in the third and last part, I will talk about a new method we developed on making membranes from cellulose nanocrystal sols. Cellulose nanocrystals are materials, nanomaterials, nanorod-shaped materials that are derived from native cellulose by degrading the amorphous regions. And basically revealing only the crystalline part of the polymer. And so I will describe how we take stable sols of these nanocrystals and form them into a membrane. Considering the challenges and needs in membrane processes, cellulose has a number of advantages. To start with, it's insoluble in many solvents, many organic solvents, including the harshest polar aprotic solvents such as NMP, N-methylpyrrolidone, DMF, dimethylformamide, and so on. This, of course, at first brings an advantage in making the membrane, because typically you need to dissolve your polymer in something to make it into a membrane. But then once the membrane is there, it's a great advantage because you can simply use this membrane in any of these solvents. Nanofiltration, reverse osmosis, and ultrafiltration in organic solvents is actually a recently and rapidly emerging area with potential applications in many industries, such as petrochemical, pharmaceutical, fine chemicals, food industries. And the biggest challenge there appears to be to find membranes that can withstand the solvents the separation is to be carried in. And cellulose there is a promising material. Second, cellulose is a very hydrophilic polymer, which is typically a good thing when you consider membrane fouling. So it fouls less, and it also fouls in a more reversible manner, which is probably why cellulose membranes are still preferred in some biotechnology applications with their very good resistance against protein adsorption. And lastly, it's a very abundant material, it's a very abundant biopolymer. In fact, everywhere we go, it's somewhere around us. It exists in plant cell walls, so you can basically find it everywhere. It's also biodegradable. And when you consider that the lifetime of a membrane module is 1 or 2 years in the food industry or so, something like 5 to 10 years in water treatment, the end of life of a membrane module is really something that we need to consider. And there, the fact that when you consider cellulose, that you can basically almost literally plant your membrane polymer, or even better, get it from food or office wastes, is standing as an advantage. Having mentioned that, actually, the major disadvantage with cellulose is also related to its biodegradability, because it's quite prone to biological attack. It's also not as resistant as many synthetic membrane polymers to extreme pHs or temperatures. But within the scope of what I'm going to tell you about, when we consider at least the last way that I will talk about for making membranes by using only the crystalline regions of cellulose, I think we may also need to revisit and reconsider this disadvantage and whether that is still there. So let's start with the first part by making cellulose membranes via phase inversion. Phase inversion is the most common way of making a whole variety of membranes, from microfiltration to ultrafiltration or gas separations. It relies on having a polymer, a solvent that dissolves the polymer, a non-solvent that does not dissolve the polymer but is fully miscible with the solvent. And in the simplest case, we start with a homogeneous solution of the polymer, either only with a solvent or in a quaternary composition, and then bring this polymer solution, either cast as a film or spun as a hollow fiber, in contact with the non-solvent, either by introducing it into a liquid non-solvent bath, exposing it to non-solvent vapor, or a combination of both. When this happens, the starting composition starts moving to the two-phase region of the phase diagram, and there's phase separation occurring into a polymer-rich phase, which eventually forms the membrane matrix, and the polymer-lean phase, which eventually forms the membrane pores. Depending on where the starting solution is compared to this binodal boundary and the non-solvent in diffusion rate and solvent out diffusion rate, the morphology of the membrane is determined. As very broad examples, if phase separation occurs in the metastable region by nucleation and growth, you get more or less like these cellular morphologies, whereas when you have phase separation in the unstable region by spinodal decomposition, you have more bicontinuous morphologies. The actual picture is, of course, much more complicated than that, but you can basically tune the membrane morphology to be a symmetric or an asymmetric membrane, microporous, macroporous, and alike, by controlling the starting composition and the rates of non-solvent and solvent diffusion. And then obviously, we need, if you're going to make a membrane by phase immersion, we need to be able to dissolve our membrane polymer in some solvent. And as I mentioned, for cellulose, this has been more difficult, but now with the developments in ionic liquids, which are molten salts, that are liquid at below 100 degrees, with the developments in these ionic liquids that can directly dissolve cellulose, this has become more easily possible. And so we made cellulose membranes from ionic liquid solutions, where our ionic liquid was this ethyl methylimidazolium acetate, a room temperature ionic liquid. We had acetone as a co-solvent and water as a non-solvent. Here you see a number of membranes and their performance. In the membrane codes, this number stands for the cellulose percentage in the polymer solution. A stands for the presence of acetone in the polymer solution, up to some 20-25%. E stands for the use of a pre-evaporation step for acetone before coagulating in water. And D stands for the use of a drying step after coagulation. So a number of things that we observed: by increasing the cellulose concentration in the starting solution, we increased the rejection to our probe molecule, which was a dye for simplicity in analysis, simply. So it was just a model molecule, bromothymol blue. By increasing the cellulose concentration, we increase the rejection. Same thing occurs when we apply an evaporation step for acetone containing solution, which actually boils down to the same thing, where we increase the polymer concentration before entering the coagulation bath. And this is actually something that's common with phase inversion. If I just go back, when the composition path enters the two-phase region from a high polymer concentration, along a tie line, there's phase separation into more of a polymer-rich phase and less of a polymer-lean phase, which eventually makes a denser polymer structure. And a drying post-treatment, if you compare this and these two, also increases the rejection to the probe molecule by means of pore collapse. All these increases in rejection were also accompanied by decreasing permeances, But overall, our membranes, which are shown in stars in this plot, together with lab-made or commercial membranes, infiltrations of bromothymol blue or other dyes in ethanol or in other alcohols taken from literature, the membranes that I mentioned here are quite comparable to other membranes reported for organic solvent nanofiltration. And the next thing we did was we tried to see the performance of the membranes with two different probes of similar size to bromothymol blue, but different charge. Here, rose bengal with a negative charge and crystal violet with a positive charge. We did this again in ethanol and in dimethyl sulfoxide, which is actually quite a harsh solvent, a polar aprotic solvent that dissolves many membrane polymers and also swells cellulose to a significant extent, but we observed no performance loss for at least weeks of filtration in any of our experiments. And then what we saw was that for when you compare these two solvents, for the same dye, the rejections were quite similar. But although the sizes of the dyes were more or less the same, the rejections were affected by the charge of the dyes, where the negatively charged dye was not rejected, but the positively charged dye was. And then we treated the cellulose membranes with the polycarboxylic acid, which partly cross-links the hydroxyl groups, but also leaves pendant carboxyl, cross-links the hydroxyl groups of cellulose, and then leaves pendant carboxyl groups that give the membrane a negative charge. Then when we did that and measured the rejections of the same three dyes in the two solvents, what we saw was that for the neutral dye, there was not much that changed, but for the charged dyes, and more pronounced in some cases, the rejections was reversed. So what was high became low, and what was very low became very high. This implies that electrostatic interactions between the solute and the membrane seem to be effective in the transport of the solutes. And what was also interesting to see is that, especially for the cases where the switch in rejection was most significant, we also saw a significant difference between the sorption of the probe on the membrane, where small rejection was correlated with high sorption here and here, as you see. Here, I should note that these rejections were measured after any sorption on the membrane was equilibrated and a stable rejection was observed. So the number that I report for rejection is actually the true membrane rejection and not affected by the sorption of the solute on the membrane. And this actually implies that a solution diffusion mechanism is governing the transport of the solutes, in that the solute that is sorbed more is more permeable. You can think of this as a solubility of the probe in the membrane, and hence a more permeable dye means a lower rejection for this dye. Until now, the membranes that I've shown were made with a solvent system that contained mostly the ionic liquid and a little bit of, not a little bit, but some acetone, but still the majority of the solvent was the ionic liquid. While ionic liquids are, of course, good solvents for cellulose, when you consider the large-scale application, their price is still quite high. And also their high viscosity, the intrinsically high viscosity of the solvent itself, for one thing, makes the processing a bit difficult. And for a second thing, it changes the phase inversion kinetics into a form that we're not used to with more conventional lower viscosity solvents. So as I mentioned, the ratio of the solvents out diffusion from the polymer solution and non-solvent in diffusion into the polymer solution is quite effective in determining the membrane morphology. And when you have a very viscous solvent in the polymer solution, this slows down the non-solvent in diffusion and then changes the membrane morphology. In fact, for all the membranes that I've shown until now, the morphologies were more or less like this: symmetric, dense to microporous nodular morphologies. This was the same when the non-solvent used was ethanol. And then we tried adding dimethyl sulfoxide into the solvent system. It's known as a good co-solvent for cellulose in ionic liquids. And then we could, in fact, add it up to a ratio of 2:1 in DMSO to amine acetate, where DMSO was actually the majority solvent, which is good for cost and viscosity considerations. But actually, if you look at the membrane morphologies, they all more or less look the same. When we look at the performance of the membranes in terms of, again, the bromothymol blue rejection and ethanol permeance, when the membranes were dried, as you see in the dark blue bars and the dark green squares, the performance of all these membranes were almost all the same for the 6 membranes that I show. However, before drying, when the membranes are used without drying, they're not only lower than their dried counterparts, as I've also mentioned earlier, but there are also differences between the fabrication conditions. So when we switch from water to ethanol as a non-solvent, or when we increase the DMSO content of the solvent system, the rejection essentially decreases. So it seems that changing the solvent system and also the non-solvent changes the morphology of the membrane. However, when we dry all these membranes, they seem to all collapse to more or less the same structure. So summarizing the first part, I've shown you cellulose membranes fabricated by phase inversion using an ionic liquid and co-solvents in the polymer solution with nanofiltration range performance. The transport through these membranes seems to be occurring through solution diffusion, and membrane solute interactions there are quite dominant. And although we can tune the membrane performance by changing the fabrication parameters, morphology-wise, all the membranes were quite similar looking, all symmetric, dense, and nodular structures. A second way of fabricating cellulose membranes is to first make membranes from cellulose derivatives and then convert them into cellulose membranes. A very common example of this is to start from cellulose acetate membranes and then in alkaline medium convert them to cellulose. Cellulose acetate you can dissolve in many different solvents and obtain in quite different morphologies. The conversion from cellulose acetate to cellulose we can watch in the IR spectra by the disappearance of this peak coming from the acetyl group, from the carbon-oxygen double bond in the acetyl group, and then the increase in the hydroxyl band here. So we could do that by varying the alkaline hydrolysis reaction conditions. And then we wanted to see if we can fabricate cellulose acetate nanofiltration membranes and then convert them into cellulose nanofiltration membranes by this time a different way of fabrication. So we made cellulose acetate membranes by a certain recipe. And then we subjected these membranes to 2 different annealing treatments at different temperatures of 80 and 120 degrees. This is actually known to densify the cellulose acetate structure, increase rejections, and decrease permeances. And this was also what we observed. We've observed increasing bromothymol blue rejections and the decreasing permeance with annealing and an increasing temperature of annealing. However, when we converted these cellulose acetate membranes to cellulose membranes, we observed a drop in rejection and a simultaneous increase in permeance. Among other possibilities, we could finally attribute this to chain scission in the alkaline medium. And as an indirect indication of this, what we tried seeing was the following. We changed the reaction conditions, so the reaction duration and the alkali concentration, obtained cellulose membranes from cellulose acetate membranes, and then dissolved these cellulose membranes in the ionic liquid and looked at the viscosity of these solutions. And actually what we observed was that the more intense the reaction, either a higher duration or a higher alkali concentration, the lower the viscosity of these solutions, implying a shorter cellulose chain. So it seems that cellulose acetate nanofiltration membranes, when converted into cellulose, don't function as nanofiltration membranes. However, these membranes or others that can be formed from conversion from cellulose acetates can perform in organic solvent ultrafiltration. This is much less explored than organic solvent nanofiltration, but still has quite a lot of potential applications. So we wanted first to see how these ultrafiltration membranes would perform in different solvents. Water as a reference solvent, dimethyl formamide, dimethyl sulfoxide, methanol, and propylene glycol methylether acetate, PGMEA, as a different solvent that we later used in a potential application. So when you consider ultrafiltration membranes, what you expect to observe is pore flow of solvents through these membranes, and then the permeance would be expected to scale linearly with the inverse of the solvent viscosity as simply expected from the Hagen-Poiseuille equation. When we plotted the solvent permeance as a function of the inverse of viscosity for these 5 solvents, we do see a trend, but the water permeance is much higher above this trend, and the PGMEA permeance is much lower. The reason we think that water has a higher permeance than would be expected from pore flow is that it swells cellulose to a much more significant extent compared to the other solvents. And then a higher extent of swelling, a higher solubility of the solvent in the means a higher solubility of the solvent in the membrane matrix. And when we consider that pore flow and solution diffusion mechanisms could be affecting simultaneously, this large extent of swelling of cellulose could be increasing the pure water permeance of these membranes to a value that is higher than would be simply expected by pore flow. When we come to PGMEA, what is likely happening has to do with the much higher molar volume, so much higher bulkiness of this solvent, and possibly steric effects at the pores. And next, we measured the molecular weight cutoff of the membrane in 3 of these solvents, in water, methanol, and dimethyl sulfoxide. So we filtered a mixture of different molecular weight polyethylene glycols through these membranes, and then when you look at these curves, the molecular weight that has a 90% rejection is expressed as the molecular weight cutoff, and we see that the molecular weight cutoff increases in the order DMSO, water, and methanol. So the membranes are most retentive in DMSO, followed by water, and then least in methanol. This does not relate to the membrane solvent interactions as we see from the swelling, but it seems to be related to the hydrodynamic diameter of the probe PEG molecules that are different in these solvents. So here you see for one of the probes of 2 kilodaltons that the size is the largest in DMSO, followed by water, and then followed by methanol, which explains the molecular weight cutoff order of these membranes in these 3 solvents. And then we considered these membranes for 2 different applications. In one of them, we started with a 1% spandex polymer solution in dimethyl formamide, and then in dead end we concentrated it up to 80% permeate recovery, so obtaining 80% of the initial feed solution as the purified solvent permeate. We had an overall average polymer rejection above 98%, and we could concentrate the polymer solution to 4%. The permeance starting from the pure DMF permeance during the filtration slowly declined and experienced a steeper decline after 40% recovery, indicating some fouling on the membrane by the polymer concentration increase at the membrane surface. However, after the filtration, when we cleaned briefly the membrane with pure DMF, we could recover about 90% of the initial permeance. So these membranes could actually be used to remove a polymer from a solvent and then reuse the solvent or reuse the polymer as well. The second potential application we thought of was one from the electronic industry, from a photolithography process. Here we worked on removing a photoresist, an oligomer SU8, as you see here, from what's called the developer solvent PGMEA. This kind of a waste stream appears in the developer bath in photolithography, where the photoresist on the substrate is cross-linked in a pattern through a mask, and then the non-cross-linked region is dissolved in the developer solvent to reveal the pattern. And then you end up with a waste containing uncross-linked resist inside this developer solvent. So we prepared representative solutions of SU8 and PGMEA, and again filtered this in dead end until a permeate recovery of 80%. We had around a rejection of close to 90%, and the declining flux down to about 60% of the pure solvent flux. And then we collected this permeate and then fed it again to the same membrane to simulate a second stage filtration with the same kind of a membrane. What we observed was a somewhat smaller rejection, but a fully recovered flux, as in the second stage, the flux was essentially the same as the pure solvent flux. So here again, we could obtain close to 95% overall rejection, starting from the feed to the second stage permeate, and a recoverable flux at the end of this filtration process. So summarizing this brief second part, I've shown you fabrication of cellulose membranes by alkaline hydrolysis of cellulose acetate membranes. We observed that nanofiltration performance of cellulose acetate membranes is lost upon conversion to cellulose. However, we obtained tight UF performance in a variety of different organic solvents. It seems that pore flow and solution diffusion mechanisms are together effective in solvent transport. And fouling observed in polymer filtrations appeared to be, at least in the cases we considered, mostly reversible. And this brings me to the last and third part of my talk, where I will describe a method of fabricating membranes by using cellulose nanocrystals. So cellulose exists in all plant cell walls, together with lignin and hemicellulose as the other lignocellulosic components, in a fibrillar form. These macrofibers of cellulose are consisting of bundles of nanofibers, which themselves consist of bundles of linear cellulose chains. In these bundles, there are amorphous regions and crystalline regions. When we subject native cellulose into a concentrated mineral acid, the amorphous regions are decomposed and degraded, and what we end up with is only the crystalline regions, which are nanorods of 10 to 20 nanometers diameter and about 200 or so nanometers length, such as those that are seen in the SEM image here and the AFM image here. When the concentrated acid we use is sulfuric acid, during this process, the hydroxyl groups on the surface of the nanocrystals are partly converted to sulfate half esters, which gives the nanocrystals a net negative charge and also good colloidal stability. So what we wanted to make use of is these stable sols, and then some interesting properties of these sols to make these into a membrane. So cellulose nanocrystals show liquid crystalline behavior. After a certain concentration in aqueous suspensions, they assemble into what's called the chiral nematic phase, which I will show in a few slides later. But what we're more interested in is that they align into what's called the nematic phase of liquid crystals when under shear. So basically they align in the direction of flow after a certain shear rate and after a certain concentration again. So what we did here is we took stable sols of cellulose nanocrystals. We filtered them on a porous support in cross-flow filtration, where they could align in the direction of flow, and we could tune the extent of alignment by tuning the flow rate. And then during this cross-flow filtration, basically form a filter cake of cellulose nanocrystals on a porous support. and then by physical or chemical means stabilize the cellulose nanocrystal cake on the support and end up with a composite cellulose nanocrystal membrane. So the first thing we wanted to see was under what conditions the nanocrystals would align. The tool we use here is polarized optical microscopy. When you have cross polarizers where the polarizing filter and the analyzer are at 90 degrees to one another, and when you have an isotropic sample, you have no light transmitted through your sample. On the other hand, when you have an anisotropic sample, such as cellulose nanocrystals in shear alignment, where the material is aligned at a certain direction, when this alignment is in the same direction as either the polarizer or the analyzer, you again see no light transmission through your sample. But when the alignment is different than either the polarizer or the analyzer, you start seeing some angle dependent light transmission. And this angle dependence is such that at 45 degrees, you would see the highest light that is transmitted. So what we did is we flew these cellulose nanocrystal suspensions inside the glass capillary, and during the flow, we observed them under cross polarizers. We did this actually at 0, 45, 90, and 135 degrees. What I show here, what the images here are those taken at 45 degrees, where the 0 and 90 degrees were all dark. So trying to see the highest light transmission when it occurs and whether it occurs. We did this at increasing shear rates and increasing concentrations of the CNC in the sole. So at the lowest concentration of 1.5%, in any of the shear rates, we see no alignment in the flow direction. When we increase the concentration, we start seeing some alignment, which increases with increasing shear rate. And at a certain shear rate, the alignment again increases with increasing concentration. Also, the color shift that you see from white to yellowish, reddish to whitish is also an indication of an increasing extent of alignment. So around this range of shear rates and concentrations, we expect the cellulose nanocrystals to align in the direction of the flow. And the next thing is to use the alignment on the membrane on the porous support to make into a membrane. And the principle that we use here is actually simply fouling the porous support with the cellulose nanocrystals. So what we know from cross-flow filtration of colloids is that when you increase the transmembrane pressure, the permeate flux does not increase linearly as it would in the case of permeating a pure solvent, but rather it increases linearly for a while, and then it levels off at what is called the limiting flux. So what happens is that at low transmembrane pressures, for the rejected species, the concentration increases at the membrane wall, which is why the permeance is lower than the pure water permeance. As you increase the transmembrane pressure further, the concentration near the membrane wall further increases, but this can only happen until a certain point, until a certain concentration at the wall, which can be the solubility limit, the gel concentration, or the maximum packing density, depending on what material you're filtering. After this point, if you further increase the transmembrane pressure, because the concentration here cannot further increase, what happens is that there starts forming a gel or a cake layer. And as you further increase the transmembrane pressure, the flux does not increase anymore, but the thickness of the deposit increases. So when you consider this mass transfer boundary layer or the concentration polarization boundary layer and do a species balance for the rejected species, for 100% rejection, this is what you end up with. So you have the permeate drag term towards the membrane, and you have the back diffusion term away from the membrane. And in the mass transfer boundary layer, these are balanced with one another. And when you suitably rearrange and integrate this expression, you can obtain a relationship between the bulk concentration at one end of the mass transfer boundary layer and the concentration at the membrane wall in relationship to the flux and the diffusion coefficient and the boundary layer thickness. After the limiting flux is reached, the two ends of the boundary layer are now at fixed concentrations of the bulk concentration and the gel concentration, and hence these are related to the limiting flux as follows: through the diffusion coefficient of the filtered material and through the thickness of the boundary layer, or as the ratio of the diffusion coefficient to the boundary layer thickness is the mass transfer coefficient to this ratio. So what we expect to see in the cross-flow filtration of a colloid is that the limiting flux should be inversely proportional to the boundary layer thickness or directly proportional to the mass transfer coefficient, saying that the higher the cross-flow velocity, the higher will be the limiting flux. And it's also expected under identical hydrodynamic conditions, it's also expected to be inversely proportional to the bulk concentration of the colloid. The lower the concentration, the higher the limiting flux. So we first wanted to see if we can observe this with the cellulose nanocrystals. We did this on two different supports. One was a dense and transparent support that made visualization in optical microscopy easy. And the second was our actual porous support that we used in the membranes. So indeed, what we see is that as the cross-flow rate increases, so does the limiting flux. Same thing for the other support. And also what was quite nice to see, as expected, was that at the same flow rate, cross-flow rate, so under the same hydrodynamic conditions, with the two different supports, we observe the same limiting flux. Only with the more permeable support, we observe it at a smaller transmembrane pressure. So then, how do these CNC layers on the membranes, on the support membrane, support layers look like? These are the polarized optical microscope images on the transparent support at increasing cross-flow rates. So what we see is that indeed by increasing the cross-flow rate, increasing the shear that the nanocrystals are exposed to, we see a larger difference in light intensity between the image taken with at the same direction as the flow direction, as is here, and when the flow direction was 45 degrees to the polarizer and the analyzer. And this difference is actually indicating a higher extent of alignment into what's defined as a nematic alignment for liquid crystal materials. At the lowest flow rate, what we see is this multicolor appearance, which is actually typical of chiral nematic liquid crystal phases, where we have aligned planes of these nanorods, but each plane on top of one another is tilted at some angle between consecutive planes. And then because the half pitch of this twist is of the order of the wavelength of visible light, we see this multicolor appearance. So the highly concentrated cellulose nanocrystal deposit on the membrane exhibits chiral nematic order. And at the smallest flow rate, this order is not disrupted by the shear, but as the shear is increased, the nanocrystal starts becoming aligned with the flow. So how to make this into a membrane? When we deposit the cellulose nanocrystals in cross-flow after a certain shear rate, we observe that they will align in the direction of the flow, and the higher the shear rate, the higher will be the extent of alignment. But when if we would simply release the pressure of filtration, the deposit would simply go back into a suspension. So this needs to be stabilized on the surface. What we have been doing until now is to do it by what we can call physical means. So we permeate, after depositing the cellulose nanocrystals, we permeate a high concentration aluminum chloride solution through the CNC layer. What we make use of here is that an increasing ionic strength would decrease the electrical double layer thickness around these nanocrystals and allow them to become closer to one another, up to a point where attractive forces between the nanocrystals will dominate over electrostatic repulsion. And the ionic strength we can control by the concentration of the salt, as well as the valence of the salt, which is +3 for aluminum here. So what you can see in the picture is what happens to the stable sol in this aluminum chloride concentration. And what we actually try doing is the same effect, but on the concentrated CNC layer on the membrane. Alternatively, this could also be tried by chemical cross-linking, which is also what we're currently working on. And this is now our membrane on the more porous, less transparent support, but we still wanted to see how the alignment on the membrane, on the porous support was. So here again, you see the flow direction, and we really nicely see that as a function of the angle between the flow direction and the polarizer, we see an increasing and decreasing light intensity, with maxima occurring at 45 degrees and so on, showing that there's alignment in the flow direction on the membranes after the aluminum chloride permeation and compaction treatment to stabilize the layer on the support. The alignment is also visible in atomic force microscopy images. Here you see the flow direction, and 9, 30, and 80 are the flow rates. At 9 milliliters per minute, we see no preferential orientation of the nanocrystals. With 30 milliliters per minute, we start seeing a little bit of preference towards the flow direction, and with the highest shear, they're mostly aligned in the flow direction. And then the next question is how this converts into the membrane performance. Here you see the rejection of 3 different probes we tested. A small one, vitamin B12 of actually not 1 but 1.3 kilodaltons of a molecular weight, a 5 kilodalton blue dextran, and an 18 kilodalton protein beta-lactoglobulin. And you see the rejections of the support, as well as the 3 membranes fabricated at 3 different cross flow rates and increasing shear. For the smallest probe with the most aligned membrane, we do see some increase in rejection, but all these rejections are quite small. However, for the larger probes, we see an increasing rejection with increasing shear rate, which is more pronounced for the middle probe, which has a partial rejection, and that is actually quite expected, since this is only partially rejecting. Any difference in the membrane pore structure will be reflected more in the rejection towards the probe. So indeed, it seems that we can align the cellulose nanocrystals with shear on the membrane as expected, but also this higher degree of alignment actually results in more and more compact deposits that increases the rejection of the membranes to the probe. So this actually provides a simple means of controlling the membrane structure by tuning easily adjustable fabrication parameters. And lastly, I want to mention that the permeance of these CNC membranes are quite reasonable compared to the rejection behavior they show. So compared to a tight ultrafiltration membrane, molecular weight cutoff, let's say from around 5 to 20 kilodaltons for all these membranes, the pure water permeances are quite reasonable. I should also note here that the CNC layers that we use as membranes here are not as thin as they can potentially be. So for ease of analysis, especially the optical analysis, the thicker the CNC layers, the easier to distinguish what's happening. But in principle, these layers can be made thinner by simply adjusting the CNC concentration in the suspensions or the transmembrane pressure, and this would be expected to increase the permeance of these membranes. And this brings me to the end of my talk. The third part I will summarize by saying that I've shown you a fabrication method for composite membranes via controlled cellulose nanocrystal deposition. We could obtain tunable performance by a simple operating parameter, that's the cross-flow rate. As I mentioned, we can further tune the performance by varying the suspension concentration, the transmembrane pressure, but also the ionic strength in the CNC suspension, which is also what we're currently working on. We could observe a reasonable permeance for the achieved molecular weight cutoffs or rejection profiles. Overall, I think this is an example of a versatile platform for membrane fabrication starting from colloidal sols. And last but not least, it presents an all-aqueous fabrication route for membranes without the need of organic solvents, which is also quite important, I believe. And with that, I would like to thank you for listening. I would like to thank all the students, first of all, whose work I talked about, Fakih, Elif, Kübra, Zeynep, Aygen, and Ceren, and all the rest of my past and present team. My collaborator in the last part, Emre Büküşoğlu, and the funding sources. And thank you very much.
Thank you, Zeynep, for this very broad presentation, and this was a very nice overview of new frontiers in membrane fabrication. I am keeping an eye on the chat on YouTube, but since there is some delay, yeah, we probably have to wait a little. Now I am receiving messages of just appreciation towards this presentation. So they thank you for this very detailed study. Yeah, and okay, we can see them. Good. We can see them in the chat. So this is a new feature I wasn't aware of. Okay, I have a question myself about the last part of your talk, the CNC based membranes. What is the stability with respect to time, but also to chemicals of these membranes as compared to the traditional ones?
That's definitely something to take care of quite seriously. So what we have done until now is to not with chemicals, but keep them in water for a while and then measure their permeances after a certain time. And in those cases, sometimes we observed similar rejections, sometimes the rejections would drop. So they're as they are, they don't disassemble immediately or even in time. But their stability definitely needs to be improved. And for that, we're actually working on chemically cross-linking them. But for the time being, what we can definitely say is that after the fabrication, we can tune the properties. But for longer term stability, we would need we would likely need chemical stabilization with cross-linking. But that's also something that's possible, so we can cross-link them. But the performance and everything, we're still working on that.
And do you think that the scale up of this type of membranes will be complicated by the fact that they need some time to be prepared?
I'm not sure if that's that big a problem. So it's so we could, in fact, that's even more or less an advantage, the way we prepare them. So we can basically just maybe, like, let's say, take ultrafiltration membranes even in modules, and then inside the module, like this could be a spiral one, this could even be a hollow fiber, and inside the module, simply by filtering the CNCs, we can form the new membrane. And then time-wise, it could be at least comparable to the polyelectrolyte multilayer membranes, and even maybe a shorter time for the fabrication. So
Yeah.
I wouldn't take that as maybe a big problem.
Big disadvantage. Okay.
Yeah.
So I'm starting to read questions from the chat. First question is about the vacuum deposition. Yeah. Maybe you can read it. Yeah. Does vacuum deposition have a disadvantage compared to cross-flow deposition for CNC membranes?
So vacuum deposition or positive pressure dead end deposition would be an alternative to cross-flow filtration. You could also think of, like, this is like positive pressure on the feed side and atmospheric pressure on the permeate side. You could also think of having still the cross-flow on the feed side, but having vacuum on the permeate, which would in fact be identical. So, like, for our purpose, it's just the transmembrane pressure that is applied. But then if you compare dead end vacuum filtration, which is very typical for 2D materials, membranes made from 2D materials, to cross-flow, then of course we need, so we have cross-flow for using like at least one adjustable parameter, that's the flow rate in aligning the nanocrystals. But then just like whether this is positive pressure on the feed side or negative pressure on the permeate side. I think that's just the transmembrane pressure for the method.
Okay, there is another question by Xenia. And do you think the technique used to produce CNC membranes could be used with other crystalline materials? I guess she refers to crystalline polymers or biopolymers.
I think it could. So as I said, it's like one example of a platform where we can use colloidal materials, deposit them on porous supports, fix them somehow, depending perhaps on the material, and then use this as a membrane. So probably rod-shaped materials would also be shear aligned under certain conditions, so they would behave the same. But even when they're not rod-shaped, but regular nanoparticles or so, they could be more or less used as a composite membrane, probably.
Okay, next one is I'm preparing inversion membranes, but they are too much brittle. Do you have any suggestion for me to make it more elastic? So this is consultancy work.
That possibly has to do with the polymer. So it's sometimes only from a single polymer. Like for instance, for PES, they're just quite elastic enough, but for others they become brittle. I believe some additives could a bit plasticize the polymer and then make it a little bit elastic.
Plasticizer, yeah. Another did try their studies with different acidic oxidation of cellulose instead of sulfuric acid, such as nitric acid or combination of nitric acid.
No, until now we're happy with sulfuric acid. We also work on further modifying it with carboxyl groups. We have not tried with nitric acid. We've been working with hydrochloric acid, but then there's no colloidal stability because they're not charged in that case. But no, we have not tried anything else.
Are you planning to study the surface properties of the CNC membrane composite, and how would you tune the surface charge, hydrophobicity, roughness?
So, well, the surface charge is a function simply of the CNC there. Of course, it can be modified. That's also quite a good thing about cellulose. So the hydroxyl groups are quite reactive, so you can modify them with many things. And the surface charge, again, you can modify with different groups. Hydrophilicity would be expected to be good with cellulose, even in its native form. It's quite hydrophilic. And then the roughness, well, yes, that's again a function of how they deposit, and likely would change with the extent of alignment, for instance. But yeah, those are of course things to consider.
Lidietta, she's asking whether you have data on the uniformity of the CNC membrane layer on a spiral wound large scale module.
No, until now, what we're working with is a lab scale cross flow module. I mean, still not too small, but we have not tried this on a spiral wound module. I think what I would prefer next to go to is the hollow fiber, because that would be really quite simple to deposit on or in the hollow fiber. If we take an existing spiral wound module, that would be quite tricky because of the spacers probably. So that would either need like a special fabrication and then making into a module. But hollow fiber, I think, will be the way to go.
Okay. I see no other questions in the chat. So there were many questions about the CNC membranes, for sure, the most innovative part. Okay, so yeah, I think we ran out of time. So if there are no other questions, I would like to thank you again for your kind response to this invitation. And I would also like to remind our followers that there is another webinar actually, foreseen and scheduled for March 2nd, so the first Wednesday of March. And the speaker will be Francesco Galliano from CNR, Italy. and it will be again on sustainable membranes. So please save the date, March 2nd at 4 p.m. Central European Time. I think there is one last question. Is there any possibility of making ion exchange membranes from them, since it has sulfonic groups?
I would be considered myself quite far from the field. I have never worked with ion exchange membranes, but maybe one could try. They could try.
Yeah. Okay, so thank you again, and thank you everyone for attending, and see you next time.
Thank you very much.
Bye bye.
Bye-bye.